Hello again. This is our fourth video for chapter 7. This one is going to cover just section 7.9, but that is going to go over two more reactions, and these are the last two reactions for this chapter. So we're going to start by looking at the SN1 reaction. Now if we just look at the name again, the S stands for substitution, the N stands for nucleophilic, and the 1 stands for unimolecular. So that tells us that we're going to do it with a nucleophile. The unimolecular part tells us that one thing is going to be happening at a time, or that one reagent is involved in that rate determining step. So here's our reaction up here. We have our substrate. Here's our substrate right here. Here is our leaving group. So all four of these reactions we're going to eventually talk about start with the same type of compound, a carbon compound with a leaving group attached. And with this reaction, we're going to react it with a nucleophile. Now, our nucleophile this time is a weak nucleophile, and the reaction is often described as a solvolysis reaction because the nucleophile is solvent. And we can say that it's a weak nucleophile because it's neutral. Weak, solvent, nucleophile, they all fall under the same category. Now, because it's a substitution reaction, our leaving group is leaving and our nucleophile is taking its place. So here's our nucleophile attached to our carbon, and here is our leaving group that has left. Now, if we look at the mechanism for this, we're going to need more steps than we had for SN2. And SN2 was considered a concerted reaction. Everything was happening at once. For SN1, we need more than one step. The first step, our leaving group leaves. This is creating a carbocation. So this is labeled as a slow step, which is, we could also say it's our rate determining step, because carbocations are highly unstable. So this is our intermediate, the product of that first step. And then in the second step, we're doing a nucleophilic attack on our carbocation. Now, because our nucleophile is neutral, when it bonds to that carbon, it's now positively charged. So the extra step that's needed here is a proton transfer. Now, we will need this the majority of the time, but it's not going to be something that we need every single time. It just depends on if we have a neutral nucleophile or not. So neutral nucleophile becomes positively charged once it makes that bond. And so then we're just using more of that solvent to bond to that hydrogen and put the lone pairs back on that oxygen. We end up with a neutral oxygen. So we have a loss of a leaving group, nucleophilic attack, proton transfer. Let's see, I think we talked about everything down here except for this third bullet point. So down here it says that we're going to create a racemic mixture. We're going to look at this a little bit in the next slide as well. Notice that it's in quotes, so it does mean that we're going to have a nearly racemic mixture. So here is our stereochemistry for our SN1 reaction. If we are starting with a chiral center, when our leaving group leaves, our intermediate, our carbocation, is going to be trigonal planar. So when our nucleophile attacks, it can attack from the front side, and we will end up with the same stereochemistry we started with, and we say that this has retained stereochemistry. Or it can attack from the back side, and that's when we end up with the opposite stereochemistry, and this is called inverted stereochemistry. And we're going to get a mixture of these two, because both sides are available to bond, and so we can say that it is mostly racemic or nearly racemic. Now, in order to use the word racemic, it means that we have to have an equal mixture of these two stereoisomers. One more word to throw in there. Notice that what we've created is a pair of enantiomers. Now, we can't use the word racemic directly because we don't have perfectly equal mixtures. So if we look down at the other picture, here is what's available. We have our carbocation, and our nucleophile can attack from either side. But in reality, our leaving group hasn't fully moved away from our substrate yet because there is still an attraction between that carbocation and that negative leaving group. So it's blocking the side that would produce the retained chemistry. So even though we're going to get both of them, the product with the inverted stereochemistry has a slightly higher concentration. The diagram on this slide is showing us our reaction coordinate energy. We have our substrate over here. After that first step, we're cation, so notice that our activation energy for that first step is very large. Our activation energy is going from here all the way up to here. The activation energy for our second step, our nucleophilic attack, is much, much smaller. So this is definitely the fast step of the reaction. Notice that our graph is divided into a blue and purple section. So these two steps are required for a substitution reaction to happen. And then if we are using that neutral nucleophile, we have this last step over here. We have that proton transfer, but it's not technically part of the substitution reaction. It's just kind of a side reaction that needs to occur with it. This first step has such a large activation energy, that's the portion that is included in our rate law. So our rate law up here, the rate is times the concentration of our alkyl halide or the substrate. So it's only involving our substrate concentration. So that means if we change the concentration of our nucleophile, it does not change the rate of our reaction. However, if we change the concentration of our alkyl halide, if we double it, the rate doubles. If we cut it in half, the rate goes half as fast. So they have a direct relationship. This is also a first order reaction because it's only involving this one chemical, and it's a first order reaction with respect to that chemical. All right, we're going to switch over to the E1 mechanism. So by the time we're done with this chapter, we will have talked about SN2, E2, SN1, and E1. So both of the S reactions are substitutions. Both of the E reactions are eliminations. Both of the 2s, SN2 and E2, occur in one step, and both of the 1s occur in 2 steps and have carbocation intermediates. So there's connections between the reactions that we can their names to see those connections. So here's our reaction. Again, we're starting with that carbon substrate with our leaving group. We're reacting it with a base because this is an elimination reaction, and we're reacting it with a weak base. And we know it's a weak base because it's neutral. And again, just like in our SN1 reaction, our weak base option is actually going to just be our solvent. And because it's an elimination reaction, we're going to lose that leaving group, we're going to lose one of our beta hydrogens, and in its place we're going to get an alkene. Here is our base that has removed that beta hydrogen, and there's our leaving group. So when we look at the mechanism for this reaction, we have the loss of our leaving group, which is our slow rate determining step, we have our carbocation intermediate, and then in our second step, we have a proton transfer. So here's our base, it's removing that hydrogen, and then the electrons are creating that alkene double bond for our final product. Now a couple things about this, it does have similar names to our E2. We can also call it a dehydrohalogenation, a beta elimination, or a 1,2 elimination, which are all describing what's happening. We're losing a hydrogen and a halogen. We're losing a hydrogen from that beta position, and the hydrogen and the halogen are on adjacent carbons. So all of those names are accurate. We stick to the E1, E2 naming because it's giving us a little bit more information. The last thing that's on this slide is the regioselectivity. Now, we have a carbocation in our intermediate here, and so when our base approaches, it can remove hydrogen from the available beta carbons. The one that's going to be removed will be the one that produces the most stable alkene. And what we learned in our first video is that the more stable alkene is the one that is more substituted. So this goes back to being the Zaitsev product. So our major product is the Zaitsev product, and this is going to result from removing a hydrogen from the beta carbon with the fewest amount of carbons. Now, when we saw the E2 reaction in the last video, we could force it to make the Hofmann as the major product by using a more bulky base. This is not true with the E1. We can't control it like we could with the E2. So the Zaitsev, that more substituted amine, will always be our major product. Let's do a practice one with this. Here's what we're starting with. We're going to start with this substrate. We have a bromine as our leaving group. So here's my leaving group, which means that's a beta carbon, and a beta carbon. I'm using a weak nucleophile or base. Our water can act as either. And so we're going to get a mixture of products here, and we're going to draw out all of the possible products. So we're going to start with our SN1 product. Now in an SN1 product, we are in the leaving group nucleophile. That's it. That's all we're doing. So the way that the product looks in an SN1 versus 2 is not any different. What's different about this is the pathway it takes. Let's look at our E1 products. Now we have 3 different beta hydrogens. The 2 left and the right are equal to each other though, because there is symmetry. So I'm just going to erase this beta carbon. We're not going to use him. So carbon on the right over here, we're going to remove one of those hydrogens. So my carbon structure stays the same. And if I lost my leaving group from here and I lose this beta hydrogen, that's my bond. Or up to the beta carbon up here and remove that beta hydrogen. So again, my leaving group left from here. My beta hydrogen was removed from here. There's a bond. Now there's one more product that we can draw. We have to consider stereochemistry. So with this product, I have my 2 methyl groups on the same side, methyl and my hydrogen on the same side. But because my intermediate is a carbocation, this bond has free rotation. And so I drew this having our ethyl and our methyl opposites from one another. So this would be the E product. But the other product that could form would be the Z product. So these are our 4 possible products for this structure. Now as we go through and talk about a little bit more information, we might be able to decide which one's major or minor. But one of the struggles with SN1 and E1 is that we do end up getting a mixture of products for a lot of these reactions. And this is kind of saying the same thing that I just said. Our SN1 and E1 are always in competition with each other. And so the major product is going to depend on the transition state. So we're talking about this transition state right here, because that first step is the same. The first step is to create that carbocation intermediate, and then in that second step, we're either removing a beta hydrogen or doing a nucleophilic attack. So for our transition state, whichever one is lower, that one's going to create a lower energy product. And so for the most part, our major product will be an SN1 product. Of course, there has to be exceptions to this. And so the exception is when we can make tri and tetra substituted alkenes. So let's go back and look at the products we just drew. And if we look at what we've created, we have our SN1 product. We have our 3 possible E1 products. This one is tri-substituted. I'm saying that because we have 1, 2, 3 carbon substituents coming off of our double bond. This is di-substituted, 1, 2. And then this one is tri-substituted, 1, 2, 3. Because we can make a tri-substituted double bond, that I-substituted will be our major product. We have 2 different to choose from. We have the E and we have the Z. The product is going to be based off of alkene stability. And when it comes to stereochemistry with alkenes, we want to have the biggest groups as far away from each other as possible. So we often say that we want to have the E or trans stereochemistry. Not totally accurate. We want to have the largest groups trans from each other. So in this case, on my carbon, the ethyl is the largest, and the carbon on the right, the methyl is the largest. So this right here is going to be my major product. So I'm just going to call this guy would be number 2 because it's also tri-substituted. This will be number 3. Substituted will be number 4. So our SN1 ranks in monosubstituted alkenes and below tri and tetrasubstituted alkenes when we're looking at those competitions. Now, because our SN1 and E1 reactions have that carbocation intermediate, we always have to keep an eye out for hydride and methyl in order to make that carbocation more stable. So in these 2 examples here, we're looking at a substrate that after it forms a carbocation is going to go through a rearrangement in order to make that carbocation more stable. So we're going to look at the full mechanism for each of these. So here's our first step, loss of a leaving group. I'm going to keep the different, but I want to keep them the same for us. Now we have a secondary carbocation. We want to make this as stable as possible. So what we're going to do is that we're going to take hydrogen and we're going to shift it over. So this is a hydride Now my carbon structure hasn't changed at all. We move hydrogen over, and now we have carbocation. So this is going to be more stable. There's my water, also known as weak nucleophile, also my solvent. We're going to do a nucleophilic attack. Again, because I had that neutral nucleophile, it's now positively charged because it has bonded to that carbocation. I'm going to use another water molecule. to do a proton transfer. And then my fixture with that rearrangement. That was a little crowded. Now let's look at the other one. So mechanism for the methyl shift. Now notice, before we move on to the methyl shift, notice that we do have drawn there with hydride shift and without shift. If a shift is going to occur, hydride or methyl, both are going to form. The one with the shift, the one that makes the more stable carbocation, will be our major product. All right, this one's not going to look a whole lot different, but it is going to show us. So we're going to start loss of a leaving group. Again, we have that secondary carbocation. We want to look at the beta carbon, so the carbons next to it, to see if we can improve our stereochemistry. So up here, if we did a hydride shift, we'd end up with a primary carbocation, so we know we don't want that to happen. Down here, there aren't any hydrogens to shift, but if we shift over a methyl group, we'll end up with a tertiary carbocation at this position. So that's what we're going to do. I'm going to take this methyl group and I'm going to shift it right over there. So I'm starting at the electrons of that and going on to that carbocation. And there's my new structure. So actually I'm going to color code this for us. Here's my methyl group that I'm shifting over, and there's its new location. So now that we have our new carbocation, we're going to do our nucleophilic attack right onto that carbocation. Labeling my steps here. And then our last step, because we had that neutral nucleophile, we need to do our proton transfer. I did that the wrong angles. Let's make it look the same. There we go. So there is our final product utilizing that methyl shift. And this has the same major minor products as the one above it. And what I mean by that is we're going to get SN1 product from that original carbocation, and we're going to get an SN1 after it goes through that 1,2 shift. If it goes through a shift, either the methyl or the hydrogen, that will be our major product. So something for us to keep in mind. We also do need to consider the solvent. So the solvent is important in these reactions because the solvent is not just the solvent, it's also acting our nucleophile or our weak base. So we have a list of our solvent options. We have the top three here are all polar protic, and then we have a polar, and then two polar A products below it. Their dielectric constant is not a number you need to know, but what it's measuring is how polar it is. So they're listed in order from most polar to polar. And then the relative rate over here is telling us how fast they're reacting. And so ethanol is set at 1, and then the others are compared to it. So methanol is 5 times faster than ethanol, and water is 40 times faster. And when we're using those polar A product solvents, it's much, much slower. So what this tells us is that with SN1 and E1 reactions, we need to use a polar product solvent. And if we remember back to when we first talked about solvents, a polar product solvent can help stabilize positive and negative ions, and forming that carbocation, we need to have something in that solution that helps to stabilize it. So our polar product solvents are able to do that, and they can help stabilize our leaving group as well, so to prevent it from reacting again with our carbocation. And then our last topic, looking at the substrate itself. So there's two things we need to look at, the leaving group and the carbon portion. With this reaction, because the leaving group leaving is the start of the reaction, we need to have a better leaving group. The list of possible leaving groups here are our halogens, and the best leaving group is the iodine, followed by bromine, followed by chlorine, followed by fluorine. So fluorine is our worst leaving group. And notice it's written farther away than the other ones to signify that it's a lot worse than others. So iodine is our best leaving group because it is the weakest base. So we want a weak base. We want something that is stable by itself. So remember, when we say weak base, that's another way to say stable base. So we want to have the weakest base or the most stable base as our leaving group. And then the bottom half of our slide here is telling us that we need to have a stable carbocation. So because our reaction has a carbocation intermediate, we can't use and secondary halides. They're too slow to react. They don't have a stable enough carbocation. So instead, we want to use tertiary, benzylic, and allylic. So benzylic is when that carbocation is next to the ring, and allylic is when the carbocation is next to a double bond. With both of these, even if they're primary, they have a lot of resonance to help stabilize them. So primary, secondary, or tertiary, benzylic and allylic will all work well for this. So our last two slides then are just the summary slides for both reactions. So we have our SN1 summary slide. This reaction up here is a little bit detailed, a little bit busy, but I like all the information that it's giving us. So we have our substrate here with our chlorine leaving group, and it's in the S configuration. As our leaving group leaves, we end up with our carbocation. I'm going to draw in our missing leaving group arrow here. Our nucleophile here can either attack from the back side, giving us the inverted R enantiomer, or it can attack from the front side, giving us the retained stereochemistry, so it still has that S configuration. The rate reaction is first order, only depends on the substrate. Our stereochemistry is racemic, but in quotes, so meaning that our inverted, so for this example, this here would have a slightly higher concentration than our retained. We want to use tertiary, benzylic, and allylic substrates only with good leaving groups. Our nucleophile should be a weak nucleophile, which is also our solvent. Generally, that means that it should be neutral, but there's exceptions to that. And the solvent that we're using, it works best if we have a polar product solvent because it helps to stabilize the leaving group, preventing it from re-reacting, and it helps to stabilize that carbocation. And then the last one here is the summary of our E1 reaction. So in that first step, we have the loss of our leaving group followed by the proton transfer. So here's the loss of our leaving group step. And then our base is remove hydrogen from our carbon to create that alkene. So this is our proton transfer step. I don't know if my writing's getting better, but it's definitely getting faster. And then we end up with a double bond as our product. The rate of reaction is unimolecular, only depends on that substrate concentration. For our regioselectivity, the more substituted Zaitsev product will be our major product, and we can't change that, we can't control that. And for the stereochemistry, the major product will be pushing those large groups as far away from each other as possible. So we normally label this as E or trans, but it definitely depends on what's in that structure. We want to use a weak base, which is usually our solvent, or something that is neutral. And again, because we're forming that carbocation, benzylic and allylic carbons with good leaving groups. All right, that is it for this video. In our next video, we're going to talk about how all 4 of these reactions are in competition with each other and how we decide which pathway we're going to take.